Hello everyone, welcome back to Random Matrix Theory. This is lecture 10. So last time we found out that each fat graph gives us a factor of something like this. And we can reorganize this in terms of the genus. Using an expression of Euler characteristic, we can reorganize this into something like this, where T is the parameter and it's equal to so we can organize or compute different quantities in the matrix model arena in terms of fat graph. Organize quantities in the MM arena in terms of fat graphs. So what does that mean? That is, any quantity in the matrix model side, we can have an expression or expansion in terms of fat graphs. That is, we can give them a fat graph representation, any quantity in the matrix model arena. So let's see an example. For example, the free energy, it's something you're familiar with. So its free energy goes like exponential f or log of z equals f and so on. This is the free energy. So what does the free energy tell us? The free energy also generates my connected diagrams, if you remember, or a free energy expansion is sometimes called the connected expansion of connected diagrams, or in physics sometimes called vacuum bubbles, whatever you want to call them. It's just the same thing. So what we can do is write the vacuum bubbles or the connected diagrams in terms of double line notation. So we can write in, let's say, double line notation. That is, we can give them a Riemann surface structure. That is, for example, if you remember, a connected diagram was like this, you can, or two of them, and so on. So you can give them a fat graph expansion like this. And so on. In terms of fat graph or double line notation, it's something like this. So now, what does the expression of free energy look like? That is the question. So the free energy at, or free energy expansion, looks something like this. This is just the coefficient, and it is weighted by the two expansion parameters. That is the sum, the sums we are doing. It's a sum over H and it's a sum over G, the genus, and this is just a coefficient. And if you want a physical representation of physical idea of what this is, it generates the symmetries. Okay, so we can reorganize this quantity. That is, we can do better. And in what do I mean by better? That is, we can do this summation and then we are left with only this summation. That is, we can define free energy F at fixed genus G as something like this: G equals 0 to infinity fg of t we have absorbed this t here. So what did we do here? We just did this expansion. That is, if we do this expansion, it's just fg 0 fg plus fg1 and so on. So we have done that expansion, and it's the expansion all the factors are absorbed into this thing, so that we have only the genus expansion. For example, at genus 0, we'll have like this 0 holes plus genus 0 scenario. So f of 0, let's say f of 0 here would look like something like this: f of 0 1 plus f of 0 2 and so on. So what we have basically done, we have just done the H summation and absorbed everything into this factor. Okay, so this is the famous genus expansion of matrix models. That is, we are doing a genus expansion for free energy. Note that we have expanded in the above scenario. We have expanded in GS. That is, we have expanded in powers of GS. This is something we have been usually doing for now, for this long. For example, if you remember, so in the one-dimensional case, if you remember, we have expanded in terms, let's give this, the one-dimensional case, we have expanded like this in powers of the coupling, or if we call the GS, let's call the GS so that it's better to understand. So in powers of, let's say, GS squared and so on. So so until now we have been expanding in powers of GS, but we can also do something different. That is, until now, or in this scenario, we kept T fixed and expanded in GS. We can do something alternative. We can expand in terms of N. That is, or more precisely, 1 over N. Which is a very equivalent scenario. It's just from the GS expansion, we are taking to the N expansion, or 1 over N expansion. So in the 1 over N expansion, again, we can keep T fixed, and since GS went as 2G minus 2 and GS is 1 over N, or from this expression GS is 1 over N goes as, so the N expansion would go as 2 minus 2G. So the GS, instead of the GS expansion here, we will have an N 2 minus 2G in the free energy expression. Okay, so another thing that we study when we are doing an N expansion, that is, we take the large N limit, or that is, we study the case when N is very large. So what happens then? So if N is very large, let's say, what happens at different genuses? For genus 0, the case, our quantities goes as N squared. For genus 1, our quantities goes as N, and for genus 2, our quantities goes as, and so on. the powers keep on, it's just the negative power of n. So if you take the large n limit, the leading contribution comes from the genus 0 case, because if you take large n, this quantity, whatever quantity you're computing, the n square contribution will dominate over, or the genus 0 contribution will dominate over genus 1, genus 2, and any genus you take. That because 1 over n squared, if you take the large n limit, it goes as 0. This becomes very close to 0, and this is just no dependence. So in the large n limit, the dominating term is just genus 0 scenario. So what is happening here? So if you take the large n limit, what the genus 0 contribution dominates over any other contribution. That is, we have genus 0 graphs are called planar graphs. So the planar graph contribution triumphs over any other genus contributions. And any other, let's say genus 1 or genus 2, are just corrections to the order, because this goes as order n squared, genus 1 goes as order 1, and this goes as order 1 over n squared, or n minus 2, and so on. So the leading contribution comes from the planar graphs. This is a limit that is often studied when we are taking the 1 over n expansion of matrix models, and in most of the scenarios we usually do the 1 over n expansion instead of the coupling constant, or a GS expansion. So now let's talk about solving the matrix model. So we usually solve the matrix models, or the matrix model partition functions, by taking them from matrices. That is, we take them from matrices to matrix eigenvalues, or to eigenvalues, because when we have matrices, even in this scenario, if it's a Hermitian matrix, you have n square real parameters, but if you have eigenvalues, it's just n parameters. So it's very easy to deal with n parameters rather than n square parameters. And since we are very familiar with the single variable or multivariable scenario of we are very familiar with variables rather than matrices when it comes to doing integration or things like that. So it's best if we shift to the eigenvalue basis, and it's almost all of the scenarios you'll be facing, we always take it to the eigenvalue basis. So before that, since taking from one basis to another is a difficult task, we study what are the things that happen when you're going from the matrix basis to the eigenvalue basis. So you start with, let's say, that is a matrix. You start with the matrix model partition function, that's the measure, and that's your function. It can be anything like, trace of m squared, plus it can be a Gaussian, or it can be whatever we want. So we are just taking a general case of f of m, and dm is the measure. Dm, you can write it like this, and it's dmii, that's the diagonal part, and the off diagonal part, 1 I less than j less than equal n, d of real mij, and d of imaginary part of mij. So this is the measure. So as you know, our matrix models are invariant or do not change if we do a unitary transformation. If we have a Hermitian matrix, if we do a unitary transformation like this, it doesn't change anything. It's the same as dealing with the original matrix M. Same as dealing with original matrix M. So we call it that M is invariant under U. So that is the unitary transformations, or yeah, under U. So in a similar fashion, the cases we have, that is f of M is invariant under U M U dagger. You can check for yourself. For example, take the Gaussian and check if it's invariant under this conjugation. It surely is. So a notation that we will be using is f u m equals f of m, and here um is just u dagger. And M is the same as, so it's just, so if you do a conjugation, you have a new matrix, that is, and new matrix is a diagonal matrix, as you know. It's just, you can write it in terms of the eigenvalues. It's something like this. The components are something like this. You can write it like, so the new matrix is something like this, or you can write in terms of M as well. Same thing. So this is what happens when you do a conjugation. That is, if you do a conjugation of the matrix M by U, you have a diagonal matrix, and it's, you can write it in terms of the eigenvalues, and delta ij is just, yeah, delta ij is, let's say, in case of 2 by 2, it's just, in case of 4 by 4, it's just the diagonal elements. So you have a diagonal matrix. We often write the diagonal matrix in terms of the deltas. So what does unitary matrices do? What is the unitary matrix you're doing here? The question is, what does unitary matrix do to M? What is it doing to our matrix M? So when a unitary transformation U is applied to M, it leads to vanishing of diagonal elements. Vanishing of diagonal elements. Because if you see, we are diagonalizing this, we are getting a matrix by a unitary transformation. If we do a unitary transformation on M, you get a diagonal matrix lambda, which is just is something like this, something, and others are of diagonal parts are 0. So this is what a unitary transformation is doing. So how do we express that? We need to introduce we will introduce something that does this job for us. So let's introduce a quantity. Introduce or define a quantity which is, let's see, something like this, and we write it or you can, if I write it explicitly, this means just 1 j n, okay, it's just delta squared um ij, or the real part of u dagger ij imaginary. So what is it doing? It is ensuring that all the off diagonal elements, what is the delta function's job? It kills an integral. So this function, the job of this function is to ensure that our off diagonal elements are killed. That is, That is, you get rid of the off diagonal elements, because when you do a unitary transformation, you are just basically diagonalizing your matrix. So we don't need the off diagonal terms. So this function does this job for us. This ensures that all the off diagonal elements are killed. So now, since we have operator this, so this is identity, because operator multiplied with its inverse, we get an identity. And also another property of this operator is this: it's invariant under conjugation by or unitary transformation. It's the same, its job is the same. So now let's see what it does to our partition function f of m. Let's introduce the operators. Since they are the identity, we can just pop this out. This is just identity. And now also note that we don't know what this is. We have just introduced a quantity which is just the inverse of this quantity, but we don't know what that is. We introduced it so that it doesn't affect our integral, because it's identity multiplying the integral, it's the same thing. Identity multiplying anything, it's just that thing. So we have introduced these two things, and f of m. So what this delta is doing, this delta function kills anything of diagonal. So it's killing anything that is of diagonal. So what we are left with is just the diagonal version of this, right? So what does that mean? I'm coming in a bit what this is. Lambda I lambda f of lambda. Or you can write in terms of, if you want, you can just write it in terms of this matrix as well. It's the same thing, because this matrix is just diagonal. So yeah, so what happened, what just happened here? We killed the off diagonal elements, and only thing we are left with is our function, our original function f of m, in terms of the eigenvalues or the lambdas. Our measure is transformed transformed from dm to d lambda, that is in terms of the eigenvalues, and this, whatever this is, it's also transformed to in terms of the eigenvalues. And this quantity is just, we have just written, this is just a normalization factor. If we have time, we'll just explicitly work out. If not, just treat it as a normalization factor. This is just the integral of du. That is, it's the integration of over unitary matrices. So now our job is, we are almost done. Our job is to find this. Then we are done from by taking from the matrix basis to the eigenvalue basis. So if you notice what happened here, since you moved from the matrix basis to the eigenvalue basis, you got everything in terms of the eigenvalues, and this term is sort of like a Jacobian term, right? It's right, a Jacobian, because of the change of variables. You change from matrix variables or matrices to eigenvalues. So it's sort of like a Jacobian, and we call this the Vandermonde determinant. Also, for those who know a bit of group theory, others it's just treated as a normalization factor. For those who know a bit of group theory, this is just the volume of the gauge group, or the group, just group UN. Other than that, it's just for others. Those who know, this is just the volume integration over the whole group. For others, it's just a normalization factor, and if we have time, we'll try to work it out. If when we study another method of solving matrix integrals, that is the orthogonal polynomials, if we have time, we'll work it out. If not, just treat it as a constant, which has a certain value. So now, need to evaluate so let us build the argument now. First, what was this? Was just du. At times I'll avoid writing this big factor. Just if I avoid it, just know that this is just this, that is I less than j, and it should be bounded between 1 and n, which is the size of the matrix. Okay. So now, since we have the freedom to diagonalize M, that is, it's invariant. It doesn't matter if you're dealing with M or the diagonalized version of M. It doesn't matter. So let's use this fact. That is, using this fact. Now we'll use something that might be familiar to some of you. That is, any unitary matrix U can be written in an exponential, in terms of an exponential. That is, you can write it in terms of a power series like this, and so on. Any unitary matrix, you can write it in terms of in terms of another matrix A, and since they have to satisfy this property, from that you can find out that A must be equal to, it's an anti-Hermitian matrix. The A's are anti-Hermitian matrix. So this is something that you do in group theory. That is, you take any unitary matrix or any matrix and do an exponential of it, and these matrices that comes out of them, they satisfy this criteria that they have to be anti-Hermitian. The A matrices have to be anti-Hermitian. So any matrix U, we can write it in a power series expansion like this. It's very easy to check this. You can check this for yourself, or you just have to Google this. So what is the property of this A matrix? The A matrix is anti-Hermitian, as you can see, or you can check by yourself, and the diagonals of the A matrices are, you can prove it, that the diagonals of A matrices are either imaginary or zero. So these are the two properties of A matrix. And about the expansion, another thing about the expansion is, the expansion is sometimes called expanding near identity, or for some of you might be familiar, this is just the Lie algebra or something like that, in a more fancy term. So okay, so this is the fact that you can expand a unitary matrix U in terms of another matrix A which satisfies this criteria. So since you have expanded this, U dagger M Q is, or U dagger equal to M, so whatever you're dealing with. So Ij equal to 0 for I not equal to j. It's obvious, right? because it's off diagonals are 0, and this is a constraint. We made the matrix diagonal, right? This is sort of like a constraint because we made matrices diagonal. You can check this for yourself, that if you take this, it always has to be 0 if I not equals j. That is, you only have the diagonal part. Now what happens to du? You can write du in terms of, this is the diagonal part, diagonal part measure, and again the pi, that is the product of real part of aij, imaginary part of aij. And here you can check that u dagger of ij, if you expand this, it's just, so what happened here, you can just check this, that is, of course you can expand, you can expand like this, and you have an expansion, so the expansion will have like this, so the expansion, if you do the expansion, and you'll see that you get a commutation relationship. One way to understand this is, okay, so think about it like this. So the unitary matrix U, we are expanded in terms of the matrices A. The matrices A are itself very small because you have A squared, A cubed. So the matrices A is very small. It's like, and A squared is even smaller, and A cubed even smaller, A4 even smaller. So what we usually do is we take the largest contribution that is coming from A and consider that. And how did we get from this line to this line? This is just aij, and you can write aij's in terms of, and whatever you have, lambda, you can take aij out. There's the delta, but it's the same thing, it's implied. So this is how we get from that line to that line. So what is happening here? Our initial integral had a delta function constraint, which will now be turned into a constraint like this, because u dagger ij, that is of diagonal parts, have this constraint that it has to be aij lambda I lambda j. We are excluding higher powers of A because A itself is very small. So we take the highest contribution, that is A. Others are very negligible. That is, if you have a quantity which is very small, let's say if you square that quantity, that's even smaller, because is an epsilon order small, that is, they're less than 0, less than 1. So if you square that, so you get an even smaller quantity. Okay, so the delta function constraint, that is it's now turned into delta squared aij lambda I minus lambda j. Now let's see what happens. And we neglected higher order terms. Okay. I forgot to write a 2 pi n. It's just a normalization factor. So it's just normalization. You understand where 2 pi n comes from, since it's Gaussian. So we normalize it like this. So sometimes you'll see that, yeah, we give a factor of 2 pi n, real part of aij, imaginary part of aij, times your delta function constraint. Du is turned into this, and your delta function constraint, which is, there's a pi of 1. Same for here, and delta squared aij. Now we are left is to evaluate this integral. So let's give a intuitive idea of how to evaluate this integral. Let me write a few comments of what is happening. Few comments. 1. We'll use this formula, that is delta of x minus xi. It's a sum over I. It's a delta function formula. You can just Google it up. It's just, so what we are doing is, here xi are the zeros or roots of the function f. For example, if you have sine x, sine x as f of x, what is your roots? They are 0, 2 pi, and so on. That is, when f of x equal to 0, what are the values that make f of x equal to 0? That's the roots. So this is what is happening. So what we have to do is break the deltas. We have two deltas, right? And what does this deltas do? That is, if, for example, if you have two delta functions, let's say you have two functions, f of x, g of y, and delta of x minus a, delta of y minus b. If you evaluate your integral, you get f of a and g of b. That is what a delta function does, right? So it will evaluate our function or pick out the specific value at a. That is what it did. That's the job of the delta function. So now what they're doing is, basically this delta function, we have two of them. This delta function is killing off this integral, is killing off this part, two deltas. That's what deltas are doing. And since we have a derivative, 1 over the derivative, you have two derivatives, so you will get 1 over lambda I minus lambda j squared. And since you're taking the derivative with respect to a, you get rid of the a's, only have lambda I minus lambda j. So you'll get a 1 over lambda I minus lambda j squared term. So ultimately what your integral will look like is something like this, n and squared. Okay, so what your, or delta squared lambda, whatever you want to write it as, it's just 2 pi minus n. This is the, or I less than j. You can use this notation as well. It just implies the same thing, square. So this is what the square of the Vandermonde determinant gives us. So ultimately what do we have? So if in terms of the eigenvalues, we have right equal to 1 to n, this factor, which we now know what this factor is, and exponential of minus 1 over 2 gs sum and lambda I squared And this factor is sometimes found out, it's a normalization factor. It can be evaluated by several methods. If we have time, we'll explore it, and by the orthogonal polynomial method. But if you want to know it, the value of this is just n plus 1 over 2 and some special function. It's called the Barnes function, and so on. It's not important because what we will be specifically dealing with is this part. This is what interests us. This is just a constant, and it's done in a lot of literatures. So ultimately, what interests us is our integral was something like this: 1 over volume of un initially, if you remember from the last lecture, dmf of m. So ultimately what this has become is to the n I equal to 1 to n d lambda I. This has become something like this, the integral, and lambda and exponential to gs. You can write it as a sum over w if we had a wm here, so the sum will be over now the eigenvalues 1 to n w lambda I. So our job will be to solve this, and we can say that for if we can find a method to for any general w, we have solved the matrix model. And we'll see in the next video that we'll be solving this by a method called saddle point analysis, and there are very useful formulas that we'll derive, and using these formulas we can solve the matrix model for any general potential. You know the formula, you just plug that in, do some integration, and you're done.